Welcome to module 27 of database management systems. We are discussing indexing and hashing mechanisms in a database, and this is the second in that series. In the last module, we have discussed the basic requirement of indexing, and we have learnt about ordered indexes using primary index, which can be dense or sparse, and the multi-level indexes. Now, in this module, we would try to look for the basis of how indexing, the index file structure can be very efficiently represented. So, we will do a quick recap of our notions in algorithms course, where we have talked about earlier balanced binary search trees. I mean, not in this particular course delivery, but I expect that you have gone through algorithms course, where you have learnt about balanced binary search trees as options for optimal in memory search data structure. And from that, we will try to understand the issues relating to external search data structures for persistent data. And very specifically, we will study 234 tree as a precursor to B plus tree, which is a very efficient external data structure for databases and index tables. So, these are the two topics to cover. So, first let me quickly take you around with search data structure. Now, I should warn you that here we are looking at a little different kind of a problem. Here we are looking at search as it is performed in the algorithms course, which mean that when you talk about data structures in algorithm course, you typically talk of data structures which have two basic properties. One, they are volatile data structures, transient, that is, they are created when the program starts and you operate on the data structure, find queries, and then as soon as your program ends, they disappear. So, they are not persistent data. In contrast, when you are dealing with database, we are dealing with persistent data, which stays even when no query is being performed. And the second, which is a consequence of the first, is the data structures that we have studied in algorithms work in memory. So, they work in a small limited space and they could be volatile, whereas the database, the data structure required for databases has to reside in the disk. So, we have seen the trade off between the on the storage hierarchy between memory and disk and other layers. So, they will be brought to memory and then certain operations done and then possibly written back and so on. So, there is a similarity in terms of the strategies, but there is a very significant difference in that because of the persistency, the data structures that are used in the database application, in the persistent data application, has to work with a very different kind of cost. So, when we talk about cost of an algorithm, say a search algorithm, we will say that a search algorithm or a sort algorithm has a certain complexity. So, the merge sort has complexity order n log n, and what it actually means is a number of comparisons you can estimate to do in sorting n numbers is approximately n times log n. But when we talk about external data structure or disk based data structure, then your cost may often not be the operations in the CPU like comparison or addition or assignment. Your cost will shift to actually the number of disk accesses, the page accesses that you have to do, because as you have already noted that the cost of a disk access is much larger, a couple of orders larger compared to the basic cost of different processor operations. So, I will start with this in this module. I will start talking about data structures which we have found to be efficient in memory, and then we will migrate to seeing how they can be used with simple extension in the as external data structures as well. So, what we have if we have given to search a key in a list of n data items, what are the different choices? I could make use of a linear search. Either the items could be in an array, ordered or unordered in an array, or they could be on a list either ordered or unordered. I can search that list sequentially and find the data item. So, I have just shown an example here. There is a couple of data items given in that array. I am trying to find 28. There are 16 comparisons that I need to do, and we all know that we can do much better if we keep these items sorted in terms of in an increasing order or say decreasing order, here it is increasing order, and then we can do a binary search, divide and conquer, and I can find the same value 28 now in just 4 comparisons. And from that we have come to the also know that this whole binary search order can be easily represented in terms of a binary tree structure called the binary search tree. So, if we compare worst case time, here again here please keep in mind that we are talking about in memory data structure. So, here the time is primarily that of comparison. So, if you look at the different data structure like unordered array, unordered list and ordered list and binary search tree, and if you check the complexity of the 3 basic operations which we will need in a database application, that is search, insert and delete, you can find that the search usually is order n unless you have a ordered array. I mean between array and list the search is order n unless you have an ordered array and you can do a binary search. The insert, the time that I show for insert or for delete is usually order 1, because when I say insert is order 1, what it means is that after I have been able to search an item which I need to insert, after I have been able to find its position, what is the additional time that you need to actually insert that item. So, that insert cost is often for unordered array and any kind of list is order 1, because you can just manipulate a couple of pointers and insert that. But if you are using an ordered array to make your search efficient, then to insert you need a order n insertion, because at the right place you need to move the elements to the right to make the space for the new element, because you need to maintain the ordering that the elements have. So, kind of we find that between the array and the list there is kind of a trade off in terms of if you want to make search better, you have ordered array and that degrades the insert delete complexity and vice versa. So, to take the benefit of both, the binary search tree is devised where you expect that the search will take the worst case order h cost, which h is the height of the tree, because that is the maximum number of comparisons that you will need to reach that leaf node. And a BST binary search tree, if it is balanced, then h would be of the order of log n, and this is what we desire. So, if we look at BST is balanced, h is of the order of log n. I am not going into the theory of proving why balancing means h is of the order of log n, or how this order of log n comes. If you have doubts, please refer to your algorithms book, you will find plenty of that. Now, that naturally, now if in the data structure, if I am regularly inserting and deleting data, then it is not guaranteed that it will remain balanced. It might, for example, if I am inserting the data in a say in increasing order in a binary search tree, then every time the insertion will happen on the rightmost node, and if it, so that will mean that I will have along the rightmost node I will have a long chain, and therefore, it will become like a linear list, and therefore, any search in that will not remain optimal, it will take order in time. So, there are different strategies that you have studied in terms of balancing. Just to remind you, there are strategies which give you the best possible worst case time of log n, which is the famous AVL tree. There are randomized strategies in terms of randomized BST, skip list. There are amortized strategies which say that I do not really care about what happens with a particular insertion, search or deletion, but what I care is if I have done a large number of insert, delete, search operations on the array, then on the average what it should be balanced, on the average it should be of order log n. So, we have seen all of these different strategies, and so in an order, in an attempt to generalize them for external data structure, we note that these are typically good for in memory operations. These are good, work well when you deal with a small volume of data. I mean, you may be, that may still be large, but it is small in the sense that the whole data fits into the memory and you can manipulate, massage the whole data in memory. And of course, all these many of these algorithms, particularly the AVL tree and quite a bit of the randomized BST, have complex rotation operations that need to be performed. or different random generators need to be involved in the randomized BST or skip list. So, there are other complexities in this whole factor. Comparison cost is not the only cost that you have, and in the simple thing is they do not scale for external data structures. They are not optimized in terms of minimizing or optimizing the disk accesses, or they do not scale to millions and millions of entries and so on. So, you need to look at a different approach, and this different approach in terms of database application, database structures is called B plus tree, and what I am going to discuss is an in-memory version of that, which is a 2-3-4 tree, so that we can understand the basic principle of such search data structure, which can work with external data, with disk data, but first understand them as an in-memory version. So, what is a 2-3-4 tree? In a 2-3-4 tree, in contrast to other BSTs, or in contrast to the typical BSTs, where every operation needs the height of the tree to be balanced, because some leaves could happen at a much deeper level, some could be at a much shallow level. In a 2-3-4 tree, all leaves always are at the same level, the same depth, the bottom level. So, height h is the height of all the leaf nodes, and that is guaranteed to be of order of log n if the tree has n number of nodes. The complexity of search, delete and insert all are order h, that is a consequence of a constant height h, or a fixed height h, that given n, that is maintained. All data are kept in a sorted order. So, if you do a in order traversal of the tree, you will get the data in the sorted order, but the difference is, in contrast to the BST, where every node is a binary node, keeps one key and has two children. Here every node, either a leaf node or an internal node, every node is one of the three types. It can either be a 2 node or a 3 node or a 4 node. A 2 node holds one data, 3 node holds 2 data, and 4 node holds 3 data, and they give the name, get the name 2 node, 3 node and 4 node based on the number of children that they can have. The 2 node can have 2 children, 3 node 3 children, and 4 node 4 children. They can generalize easily to larger nodes, which can have a large number of different types of nodes, and it extends very naturally to external data structure. So, that is the basic about the 2-3-4 tree. So, let us just go through it in a little bit more detail. It uses 3 kinds of node, as I have said, and now let me just show you. So, if we are talking about a 2 node, so this is a 2 node. So, there is one data item S, and all search keys which are less than S are on this side, all search keys which are on greater than S are on this side. We are just, for the simplicity of discussion, we are assuming that all keys in this data structure are unique. So, there is no repeated keys. The repeated keys can be handled in a very easy manner. So, this is one type of node. A second type of node is a 3 node, which must contain 2 data items S, we are calling it S and L, and 3 links. The first is less than S, the last is greater than L, and the middle is greater than S, but less than L. So, which means actually what we enforce in terms of the 2 keys that exist at the node, S must be less than L. So, values less than L go on one link, values between S and L go on the middle link, and values greater than L go on the third link. Similarly, if I have a 4 node, here I have 3 values where S is less than M is less than L. So, now you can understand why the acronyms S, M and L, small, medium and large. So, on the end we have 4 links. The first link gives you values less than S, second is between S and M, third between M and L, and fourth greater than L. So, these are the 3 different types of nodes that a 2-3-4 tree can support, and if it is a leaf node, then it can contain either 1, 2 or 3 data items. So, let us go forward. Now, to search. To search is a simple extension of BST. You know how to search in a BST. You start with the root, see whether the given key to search is greater than the key at the root. If it is greater, you go to right, if it is less, you go to left, and you do the same thing here for a 2 node. For a 3 node, all that you need to find out is between S and L, whether it is less than L, then less than S, then you take the leftmost, whether it is greater than L, then you take the rightmost, if it is between S and L, you take the middle. Similar strategy you do for 4 node, and search is a simple extension of the BST algorithm. So, you can certainly work it out. Now, what do you need to do in terms of an insert? Insert is very interesting. So, for insert, first you search and find the expected location where you are expecting it. So, that is not there. So, you will expect. So, now what are the possibilities? The possibilities where you have found the expected location, that node could be a 2 node. If it is a 2 node, all that you simply need to do is change that to a 3 node, insert the second item. If it is a 2 node, it has only one item. So, just insert this new item there and make it into a 3 node. Good. In the second case, if you find the location, if you find that it is a 3 node, so it has 2 items, you just change it to a 4 node and insert this as a third item. Obviously, when you insert, you will have to decide as to where you should insert. That depends on whether your given key is greater than the key that already existed or smaller than that, and so on. Now, the question is what happens when if you locate the place to be insert itself is already a 4 node. Now, naturally you do not have anything bigger than a 4 node. So, if it is a 4 node, then all that you need is to split that node. You have to split the node. So, you have a 4 node. So, you have a 4 node. So, you have a data 1 here, you have data 2 here, you have data 3 here, and you know that your D has to get inserted in this. So, you cannot insert it by changing the node type, because it is a maximum allowed. So, all that you want to do is to change that into a different structure, and that structure is called a node splitting structure. So, we will see in the next slide as to how this is done, and we will see how different splitting sequence can happen, and what will happen when a 4 node will split when it was a root or the different kinds of parents that it has. Let us just go there. So, what we are saying is suppose you have a 4 node which is a root. Now, splitting that is actually doing this. So, you have to convince yourself that in F234 tree, what we have already assumed, whether I represent this or I represent this are algorithmically they are equivalent. So, a single root 4 node and such a structure of your 3 2 nodes are equivalent. Why is it so? For example, if you are looking, say if you are looking for A here, then it is say it is less than S. So, you come here. Now, if you are looking for the same A here, what happens? A is less than S. So, it must be less than M. Remember, S is less than M is less than L. So, A is less than M. So, you take this part, it is less than S, so you come here. Let us take a case of C, let us say C. So, if it is C, you should come here. Now, if you check here, C, if it is falling on this link, that means it is greater than M and it is less than L. So, it is greater than M, you come here, it is less than L, so you come here, so you reach the same link. So, you can see that actually a 2 3 4 tree is not a unique representation. Depending on the requirement, I can replace 4 nodes in terms of other 2 nodes and actually create a new tree configuration. So, if it is at the root, I can get rid of a 4 node and replace it by this equivalent tree. Now, suppose the 4 node is not at the root, it is somewhere else. So, what are the possibilities? If it is not at the root, it must have a parent. Now, the parent could be a 2 node. So, if it is a 2 node, then these are the 2 possibilities. If it is a 2 node, then so this is a parent node which is a 2 node. So, then the 4 node could be a left child of that or it could be a right child of that. If it is a left child, then we will split, take the middle item and insert it in the parent. and by that process the parent becomes a 3 node from a 2 node, and make these become 2 different 2 nodes. Again, the way I was just explaining in the previous slide, you can convince yourself that these structures are equivalent. For example, if I am looking for D, let us say, if I am looking for D in this tree. So, if I am looking for D, that is greater than L. So, how do I arrive here? Now, since this is the left child, so it must be less than P, otherwise it could not have occurred on this side. So, it is less than P. So, D is less than P, D is greater than L. So, given that if I search for the D here, so it is less than P, and since it is I also have from this the D is greater than M, otherwise it would not have come to this third link, this fourth link, it would have been elsewhere. So, I know that D is greater than M, so and it is less than P. So, if I combine these two, then D has to go on this middle link, because it is greater than M and less than P, and then I have it is greater than L. So, it has to be on the right. So, it comes to the right position. So, in this way you can convince yourself in every such case that if the parent is a 2 node, then you can equivalently split the 4 node and make an insertion in the parent 2 node, convert it into 3 node and get rid of the 4 node altogether. That leaves us with one other case, which is if the parent is a 3 node. Naturally, if the parent is a 3 node, then there are 3 possibilities now, because your 4 node could be a left child, a middle child or a right child, and in every case you do the same thing, you split the 4 node, take the middle item, put it to the parent. So, parent converts from 3 node to 4 node now, and your rest of the split and pointer adjustments are done, so that you get rid of this. So, what happens in this process, unlike the earlier ones, here you do not get rid of the 4 nodes altogether, because in replacing one 4 node you are creating another 4 node, but in the process what is happening, the 4 node is moving up, it is going one level up. So, again what we will do is in recursively the new parent 4 node parent will again be split, and as you split, if it is its parent, that is parent of the parent, if that parent is also a 3 node, then that will become a 4 node. This will continue till your root becomes a 4 node, and we know that when root becomes a 4 node, I can always change it to a configuration of 3 2 nodes. So, in this process, as we have shown that we can actually get rid of the 4 nodes in the whole of the 2 3 4 tree when it is required. So, the basic strategy is very simple, that we will keep on constructing the 2 3 4 tree, and whenever we come across a 4 node for the first time, we will split that and rearrange, so that you can get rid of it. So, here what I show you is basically an insert sequence over the next couple of slides, which is trying to insert the data in this following order, starting with an empty 2 3 4 tree. So, we first insert 10. So, you get this, then you insert 30, that is here. So, 2 node becomes. So, here the convention that I am following is blue is a 2 node, green is a 3 node, and red is a 4 node. So, then you insert 60, it becomes a 4 node, and as soon as it becomes a 4 node, the next element to be entered is 20, but before that this 4 node will have to be split, and this is a case of splitting at the root, because this has no child yet. So, you split and you get the middle moves to the top here as 30, then you have 2 children 10 and 60, and after the splitting you move on to actually inserting the intended 20 into it. So, 20 gets inserted on this side, 20 is inserted on this side because it is smaller than this and comes here. So, this 2 node becomes a 3 node, then you insert 50, which goes on this side, and gets inserted here. So, your insertion continues. Your next to insert is 40, which gets inserted here, it becomes a 4 node, and as soon as it becomes a 4 node, and before the next insertion of 70 can happen, you need to do a split. So, you do a split. If you do a split, then your 50 moves to the parent, this becomes a 3 node now, and your 40 and 60 becomes 2 node children as is. So, it is the same information is represented, but now in this new 2, 3, 4 tree you do not have any 4 node. So, you now can go ahead and insert 70. So, insert 70, 70 gets inserted here, the 2 node becomes a 3 node, this is done. So, then you insert 80, 80 gets inserted here, it is greater than, it comes here, and this becomes a 4 node. And so, naturally the next would be to insert 15. So, 15 goes in onto the left. So, 15 has come in here, which becomes a 4 node, and the next is to insert 90. So, which has to get inserted here, it should have got inserted here. So, this is already a 4 node. So, you need to split. So, you split, and as you split you get 40, 40 was already there, you get 60 and 80, and the 70 that existed in the middle goes to the root, and your root becomes a 4 node. So, this is the configuration you move on to. Your 90 gets inserted. Now, you have to insert 100. So, you before that this your root has become a 4 node. So, you do a split. So, as you do the split, this is a new configuration that has happened, and this is what has resulted from the split of this 4 node at the root, and then naturally you can go ahead and insert 100, and 100 is now inserted here. You could do adjustments of changing this this 4 node into by splitting it and moving it onwards. I have not shown that, but if you now go back, if you just now go back on these this whole process, and you will see that specifically that we claim that all leaf nodes would be in the same level. So, you can see that initial 3 trees all are at the same level, their leaf and their level 0, and then when you have had a split, then the leaf nodes 10 and 60 are both at level 1. So, you can see that when actually you split at the root, you add 1 level to all the leaf nodes, and that is the only time your height changes. So, beyond that you will look at this, the level has not changed, I am going to the next, the level has not changed, it remains to be height 1, level does not change, height 1 does not change till the left here. And then we have a case again of splitting a 4 node at the root, when the 1 level has been added to all the. So, all the leaf nodes were at level 1, now all of them are at level 2. So, in a 2, 3, 4 tree you achieve this invariance of all leaf nodes being at the same level by maintaining that the only time the height changes is when you split a 4 node at the root and add 1 level uniformly to all of them. And then rest of the logic is quite simple, that these are here, you can do actually follow the same logic as of the binary search tree analysis, that if there are n items here, then the maximum height could actually be order log n, because we though all nodes are not binary, but the nodes that are not binary actually have more data. So, they will be the height will always be log n or less than that. Of course, there is an issue of concluding the complexity, because now you will argue that there are 3 nodes or 4 nodes where more than one comparison is required to decide about the node. But the counter argument to that is, even if that be the case, even if you have along the path of the tree from the root to any leaf node, even if all of the nodes are of R4 node, that cannot happen, as you have seen, because you will keep on splitting and distributing that. But if all of them are 4 nodes also, then what you will add is simply a factor of 3, 2 rather additional with the log n, and the overall complexity remains to be log n. Now, if you have to delete, you have to do very similar operations. I have not shown the details, but you look at the node and then actually find the in order successor for that and swap it with the item, and then you can do the other arrangements of collapsing the nodes. As we have done the splitting of nodes, now we have to do the collapsing of nodes following the same reverse structure. I will leave that as an exercise to you, just work it out at home. So, if we look at the 2, 3, 4 tree, and this is a time to justify why we are doing this. All leaves are the same depth, which is a great advantage. The height is order log n always. Complexity of search, insert, delete, all are order log n. All data are kept in sorted order. It generalizes easily to larger nodes and extends to external data structures. So, what do you mean by larger nodes? Let us look at that a little bit. Before that, of course, 2, 3, 4 tree has a major disadvantage compared to binary search trees of the other kinds, because it uses a variety of node types. So, when you change from a say 2 node to a 3 node, you actually, if you think in programming terms, you have a lot of additional cost, because you need to destruct the 2 node and create a 3 node. If you split a 4 node and create 3 2 nodes as required, then you have to destruct the 4 node and create 3 2 nodes. So, there are a lot of overheads in terms of that. So, what if we just simplify that process, and if we assume that there is only one node type which has enough space for 3 items and 4 links, and we do not have 2, we functionally there will be 2 node, 3 node, 4 node, but physically let them be the same type of node. So, any internal node can have what is the specification. So, they are the same type. Any internal node has 2 to 4 children, and a leaf node has 1 to 3 items. That is what all that we are saying. So, by doing this, we will waste some space, but we have several advantages, particularly when you look at this for external data structure. So, what will happen is, if I can think about 2, 3, 4 tree in that manner, then I can obviously generalize that it is not necessary that I will have to restrict myself at 4 links, 4 children. I can do more than that. So, in general, I can say that a node has n children, and it is each node is not a leaf, not a root or a leaf, will have between n by 2 and n children. So, put n as 4, you will find that it becomes 2, 3, 4 tree. And a leaf node will have n minus 1 by 2, which is 1, and for n of n being 4, and n minus 1 or 3 values, which is what do we have. So, if we just generalize from 2, 3, 4 to n by 2 to n, and have a container, have a node container which can have either n by 2 or n by 2 plus 1 or n by 2 plus 2 or maximum up to n minus 1 data items and corresponding number of children, then we will be very easily be able to arrange for a similar data structure which will have all the nodes, all the leaf nodes at the same level. And so, this is the structure which is which extends very easily, and this is the fundamental structure of what we say is a B tree or a B plus tree. We will see the differences shortly, but this is a basic notion, and the strategies of node splitting and node merging in case of deletion, and the algorithm of insertion deletion that we have discussed here will simply get generalized in case of B tree when we go to the next module. So, we have recapitulated on the balanced binary search tree, and we have introduced the notion of a 2, 3, 4 tree, which is a precursor to B plus tree, B tree, which are efficient external data structures, and will be covered in the next module.